So good afternoon, everybody. So it is my pleasure to welcome here Damien Gagnier from Institute of Theoretical Physics in Charles University Prague, and he is going to speak about this project.
Okay. Well, first of all, thank you for the invitation. So yeah, today I'm going to talk about this, which is a complicated title. It's not really necessary, but I will talk about common envelope evolution, basically, in binary stars. So just as a quick introduction, because maybe you don't know what common envelope evolution is. So common envelope is basically a phase in the life of binary systems when one of the two stars expands, initiates some unstable mass transfer onto the more compact companion, and ends up engulfing it. And once the secondary star here is inside the primary's envelope, it will rapidly spiral in towards the core of the primary star, and this phase is called the dynamical in spiral. And then two things can happen. So the first option is that this leads to a prompt merger. So the two cores, so the secondary star and the core of the primary star will merge. And if that's the case, then the system will just keep evolving as a single star, basically. So this is not very interesting, at least not for me. And the second option is that eventually this rapid in spiral can stall. And then the big question is, so like what happens after this in spiral stalls? Okay, so what we know from observations, or what we expect actually, is that in the end, like somehow we should end up with a closed binary system at the center here, and with the ejection of the envelope. But so how do we get from the in spiral stall to this stage? So the common view of common envelope evolution is that the system reaches a self-regulated phase. So that means that once the spiral in stalls, the drag that the secondary star will experience will be very weak, and this will cause some dissipation of heat, and this dissipation of heat will reduce the local density, which will reduce the drag, which will increase the density, and so on and so on. So in the end, you end up with orbital contraction here and the ejection of the envelope on a thermal timescale. But of course, because this phase is on a thermal timescale, it's extremely long, so it has never been simulated in hydro simulations, so basically it's just a guess. This self-regulated phase, we don't know if it exists or not. Okay, and in the work I will present today, I will look at the effect of accretion to see like if the two cores accrete matter, if it changes something or not, or what happens if you don't have accretion. So two extreme cases. So first, just some very brief introduction on what has been done before. So this is just a simulation of the unstable mass transfer, so what happens right before the common envelope phase. And this is a simulation of the dynamical in spiral, so the rapid in spiral. So as you can see, like simulations have been only done in these two regimes, so the rapid in spiral and the unstable mass transfer. But no one has simulated what happens after this phase, basically. And of course, all of these simulations that I showed two examples have limits. The first one is that they initialize their system with arbitrary orbital parameters. And usually they assume that initially the orbit is circular and synchronized. So the rotation of the primary star is like synchronized with the orbit of the secondary. So basically they assume that you have a very efficient tidal dissipation, which means that your circularization timescale and synchronization timescale are very short compared to the expansion of the timescale associated with the expansion of the primary star. Okay, and of course, like assuming initial circular orbit is like a very strong assumption, in particular because it has been shown that if you have an initially eccentric orbit, you can have very different results and very different outcomes from the common envelope evolution. And another limit of these hydro simulations is that they always stop right after the rapid in spiral finishes. And there are two reasons for this. Of course, the numerical cost, so you cannot simulate your system for like an infinite amount of time. And maybe the most important one is that it has always been assumed that the phase that follows this rapid in spiral occurs on the thermal time scale, which is very long. So people really did not bother to simulate this phase, even though this has not been proven. So yeah, let me just quickly present the objectives of the work I will present today. So what we have done is basically simulate for the first time this later phase of evolution, so after the dynamical in spiral. And we wanted to answer 3 questions. So the first one is maybe the most important one, is to look at how the binary separation evolves and on what time scale. So is it a thermal time scale or is it something shorter or something longer? So we'll see that in the next few slides. And the second objective was to look at the typical variability of the mass accretion. So this is particularly important because we wanted to compare it to what happens in circumbinary disks. So in circumbinary disks, basically people have shown that you have some characteristic frequencies for the mass accretion rate. You have like some very distinct frequencies that are associated with the variability of mass accretion. So we wanted to see if we have the same in common envelopes. And the last question is to look at how angular momentum is transported inside the common envelope. Okay, so of course to do this we had to do lots of assumptions. So the main point is that we assume that in the vicinity of the binary here, when the dynamical in spiral stalls, the binary will virialize the gas, and this can lead to 2 extreme cases of accretion. So the first one is that we have like a virialized gas bubble that will pressure support the envelope like this, and that will prevent accretion. So in this case, you don't have any accretion. And the second extreme case is that there is an efficient mechanism that will release the pressure at the center here, the virialized gas bubble. So this could be jets, for instance. Of course, if it's jets, you have to account for the feedback of the jet on the dynamics of the envelope and on the accretion. And so if you have this very efficient pressure mechanism that releases the pressure, then the mass and the angular momentum from the envelope will flow freely towards the binary. So the binary will be able to accrete. Okay. So for our setup, we used for our simulation we used the Athena++ code in spherical coordinates, and we also made use of its adaptive mesh refinement capabilities. And so what we did is that we start with a simple setup like this, basically an envelope, binary inside an excised region here. And depending on the boundary condition that we enforce on this excised region at the center, which mimics this virialized gas bubble, you will have one or the other extreme case of accretion. So if you have reflecting boundary condition, then you will not have accretion. If you have outflow boundary conditions, then the mass and angular momentum will flow freely towards the binary. So to initialize our system, we just simply assume that the envelope initially, well, I will explain later what we do next, but initially the envelope is in hydrostatic equilibrium. So for the binary potential, to initialize our profile, we just derived the first order correction for the binary potential, which is just the quadrupolar component of the binary potential. So with this, we just have like our initial pressure and density profile. And of course, because we only focus on the later stage of common envelope evolution, we do not model the rapid in spiral of the secondary star. We start when the binary is already close, like the 2 cores are very close together. We have to somehow mimic what happened before. And to do this, we use the technique that has been introduced in some paper before, where we just inject angular momentum in the envelope initially, up to some target value that looks like this, where the beta here is, we can vary it to vary the amount of angular momentum that we inject in the envelope. And once the envelope has been spun up to the desired value, then we replace the average potential that I showed before with the real potential of the binary. And when you do this, you actually see that you have a small bump of internal energy, and that accounts for the injection of energy from the secondary into the envelope. Okay, so this is not really important. Okay, so, oh yeah, I forgot. I need to start the video because it doesn't work for some reason. Sorry. Okay, so basically this looks like this. So we spin up the envelope. We replace the binary, the average potential with the real potential. And then we let the system evolve towards a secularly evolving quasi-steady state, basically. Okay, so this is just how it looks like. So this is just the density. Okay, can I? Oh, okay. Sorry. Okay. Okay, so now, okay, let's first start with the first point. So looking at how the binary separation evolve in our system, depending on the accretion regime, either we allow accretion or we prevent accretion. Okay, so let's divide the problem in the two cases. So in one case, we allow accretion. In the second, we prevent accretion. So the first thing we wanted to look at, and it's often very obvious for people studying common envelope evolution, is whether the binary contracts or expands. So people studying common envelope usually always assume that the binary contracts, like it does not expand. So this is the first thing we looked at, just to be sure that the binary contracts and does not expand, because in this case it would not be in agreement with observations. So when you have accretion, the evolution of the binary separation, so which is the A, B here, just simply looks like this, where the m dot here is the mass accretion rate onto the binary, and this J dot is the evolution of the binary angular momentum, the time evolution. And this has two components. The first one corresponds to the angular momentum accretion onto the binary, and the second one is just the gravitational torque, so the transfer of angular momentum from the binary orbit to the envelope, or from the envelope to the binary orbit. If you don't have accretion, of course, it's even simpler. It only depends on the gravitational torque, because you don't have accretion, so you don't have this m dot, you don't have this accretion term here. Okay, okay, so in the case of accretion, you can introduce this small j, which is an angular momentum or specific angular momentum transfer rate. And it's simply derived from this equals 0. And from this you can obtain like this condition. So if this quantity, this j is larger than 3/8, then the binary will expand. And if it's smaller than 3/8, it will contract. If you don't have accretion, of course, it only depends on the sign of the gravitational torque. Okay, yes, so actually in circumbinary disks, there are lots of parameters that lead to the expansion of the orbit, and this is why we were interested in looking at making sure that it contracts and it does not expand, like it can be the case in circumbinary disks. So here is just something that illustrates this difference between common envelopes and circumbinary disks. So on the left you have the mass accretion rate, so this is the angular distribution of mass accretion rate onto the virialized gas bubble, the inner sphere at the center of our domain. And you just see that, well, most of the mass accretion occurs on the equatorial plane, so on the orbital plane. But you have some mass accretion near the pole too. And of course, if you look at the specific angular momentum accretion rate, at the pole it's 0, because if you accrete mass from the pole, it's not rotating and it has no specific angular momentum. So you only accrete angular momentum from the orbital plane. And so if you have a disk, for instance, instead of something that is spherical, you will not have mass accretion near the pole, because there is nothing above and below the binary. But if you have this spherical problem, so a common envelope, you can have much more mass accretion than angular momentum accretion. So this tends to lead to a smaller value of J, so to contraction of the orbit. Okay. So just let's look at some results. So here on the first panel, it's this J, so this specific angular momentum transfer rate. And the horizontal dashed line corresponds to the value of 3/8. So if you have something that is larger, the binary expands, and if it's smaller, it contracts. And the different colors here corresponds to different value, so different initial angular momentum in the envelope. So different beta, if you remember the expression of the target angular momentum. Okay, so the first thing that we see is that for all of our model, after a while, everything basically, the orbit always contracts, whatever the amount of angular momentum that we initially put in the envelope. So that's good news, that's what we expected. On the second panel, you have this gravitational torque. So the black curve corresponds to a case where you don't have accretion, and the blue one corresponds to a case where you do have accretion. And something that is obvious from this figure is that when accretion is allowed, this gravitational torque rapidly reaches 0, basically statistically 0. But when you don't have accretion, this gravitational torque remains positive and slowly decreases. So I will not explain why it's so different between allowing and preventing accretion, but if you have questions later, maybe I can talk about this. But what I wanted to show from this figure is that, okay, the gravitational torque when you don't have accretion is positive, so it also leads to accretion. So if you allow accretion, you have contraction of the orbit. If you prevent accretion, you also have the contraction of the orbit. So, okay. And maybe the most important part of this figure is this last panel, where is represented the time scale of orbital contraction. So what you can see, or maybe it's not that obvious, is that when you allow accretion, so that's the colored lines, this time scale reaches some almost steady value, which is of the order of 1 to 10,000 orbital period. And this time scale for contraction is actually much smaller than what is expected, which is the thermal time scale that I discussed before. So it's orders of magnitude shorter than what is actually expected in this system. But when you prevent accretion, when you don't have accretion, so that's the black line, this time scale is also initially quite short, but it never stops increasing. And I can also discuss that later if you have questions. And at the end of our simulation, it reaches something of 10 to the 5 orbital period, which is typically of the order of the thermal time scale. So that means that at this stage of evolution, you cannot really assume that the common envelope evolution is a adiabatic process, and you have to account for different processes, and basically you can no longer the results from your hydro simulation are no longer make sense, basically. So you reach this self-regulated phase. Okay. Okay, so now I will look into a bit more details on the mass accretion variability and try to see how it compares to circumbinary disks. So this is a space-time diagram of the mass accretion rate onto the inner boundary. So here you have the colatitude. So on the top it's the pole, and on the bottom it's a north hemisphere here and south hemisphere here, if you want, and the equator is in the middle. And from this figure, so this is the local mass flux, you can see that you have like some very strong variability of mass accretion with time. And you can also like distinguish like somehow two different regimes. That you can see that there are some difference between these two regimes, and it will be more obvious in the next slide. Sorry for the animations. I'm discovering PowerPoint. Okay, so that's just the same things that I showed before, the first panel. So this is the first regime that was on the left, and the second regime that was on the right. The second panel is the total mass accretion rate. So this is the integration of this quantity at every time. And the last panel is the power spectral density, so the Fourier transform of, so in black line is the Fourier transform of the global mass accretion rate. And in colored lines, it's also the power spectral density, but each color corresponds to one region in latitude. So I don't remember which color is which, but it doesn't really matter. So one color is basically near in the northern hemisphere. Another color is in the southern hemisphere, and the third color is somewhere like in a range somewhere around the orbital plane. Okay, so the first thing, like whatever the regime you look at, that is quite obvious, is that there are two main peaks. One at orbital or a frequency of 2 times the orbital frequency, and another one at 0.2 times the orbital frequency. So this frequency is to be expected because it corresponds to the forcing frequency associated with the quadrupolar moment of the potential. So this was expected. But this 0.2 frequency is also actually present in circumbinary disks, surprisingly. And it corresponds in circumbinary disks to the formation of overdensities in the envelope. And this frequency corresponds to the orbital velocity of these overdensities. I will show a video later if I can. Okay, and another thing to look at, like what distinguishes these two regimes, is that in the first regime you can see that there are some like tilted lines like this, and this is due to some accretion streams that like hit the binary in the northern hemisphere, and then they migrate toward the southern hemisphere. And because of this, if you look at the power spectral density of the global mass accretion rate, so the black line, you can see that this 2 omega peak does not appear. And this is simply due to this asynchronicity of the mass accretion rate. So if you integrate this, you will see that it will basically smooth out the variability. So that means that if you want to look at this mass accretion variability in a spherical system, like common envelope, you have to look at it locally, like at different latitudes. Otherwise, you miss this peak, basically. Okay, so now there are 2 videos. Sorry, so they're all supposed to be played at the same time, but of course I won't be able to. But it's fine. Okay. Okay, so one thing that so this video illustrates. It's a simulation of circumbinary disks, and this is this overdensity that maybe I can loop. Okay, it's in Czech, so I don't know. Okay, so yeah, so the 0.2 frequency is just the orbital frequency of this overdensity that form and that remain at the same radius, basically in circumbinary disks. And these overdensity, actually, they form because of some of the accreted matter here will be flung back into the envelope, and this will form these overdensities. Okay, and now if I look at what happens in our simulation, so if I look at the same quantity, well, yes, it's a bit more messy, but you can still see that we also have a similar kind of overdensity, so non-axisymmetric overdensity. But in circumbinary disks, you saw that it remains at the same radius and it orbits at this specific frequency. But in our case, it just propagates outwards in the envelope, and the 0.2 frequency is not associated with the orbital velocity of this overdensity, but just with the formation and destruction of successive overdensity. Okay. Okay, now I need to find a way to not start from the beginning. I don't know how to do it. Okay, thank you. Okay, so this quantity that I showed in the two videos is the surface density. So of course, if you have a disk, this surface density is basically just the integration from minus infinity to, well, from z equal minus infinity to infinity. So in the perpendicular direction from the disk. But if you have a sphere, it does not work like that. So we only show that what happens around the orbital plane, but basically it's the same thing. Okay. So this, you have to remember the video that the last video I showed you. So this is supposed to be here. And on the right here is another space-time diagram of some quantity here that is a proxy to the non-axisymmetric overdensity that I showed before. And here you can see it more like it's clearer like this. Or the first density here, the first frequency you can see here, you can see that there are some strong variability near the boundary. And this is the 2 omega frequency. And the 0.2 frequency is associated with the formation of overdensity. So here, this is an overdensity that has formed before, somewhere here. And that propagates outwards. And this is another overdensity that is forming here. And instead of orbiting around the binary at a constant radius, it propagates outwards in the envelope. Okay, so another interesting thing to look at is the same thing, but for the eccentricity. So we look at the space-time diagram of the eccentricity. So the envelope eccentricity. And one thing that you can see when comparing these two figures is that you have a maximum eccentricity where you have a minimum. Well, you don't have overdensity, and this is due to the fact that the gas that is located in between two successive overdensity. So the eccentricity of this gas will amplify. So this is trapped. It's called trapped eccentric modes. So the modes here are eccentric modes are trapped, and it will amplify the eccentricity of the envelope. Okay, so now you can also look at the total eccentricity of the envelope, and for like all of our models. And what's interesting is that you see that after a rapid exponential growth of the eccentricity, you see that whatever the amount of angular momentum you have initially in the envelope, they all reach an eccentricity that is roughly the same, and that is maintained throughout the evolution. And that means that whatever the mechanism excites the eccentricity, it is in equilibrium with what damps the eccentricity. And so basically, because of this, you can expect that in the subsequent evolution, this eccentricity should remain constant. And of course, if you compare with circumbinary disks, typically you have the same thing in circumbinary disk, except often it does not lead to a constant value, but it depends on the parameters. But the exponential growth, the initial exponential growth, is typically the same in circumbinary disks and in common envelope. Okay. So now let's just talk a bit about the angular momentum transport in the transport here in the envelope. So first, if you remember the first video I showed you, I will not show it again. It's very clear that it's very unstable. The flow is very unstable. So just to make sure and to look at it in slightly more detail, we looked at the Solberg-Oiland criterion for convective instability. So this is actually a very simple criteria. It's just so basically if these two terms, the sum of the two terms is positive, then you expect convective stability, and if it's negative, it's unstable. So the first one is the Rayleigh, it's the Rayleigh frequency. So it characterizes the stability of the envelope with respect to the gradient of angular momentum. So depending on the sign of the angular momentum gradient, it's stable or unstable. And this is the Brun-Weissala frequency. So this is just basically the density stratification. Depending on the sign of the density gradient, it's stable or unstable. Okay, so if you look at this quantity in our simulation at two different time steps. So the first one, so this is the orbital plane, and this is perpendicular to the orbital plane. So this is early in our simulation, and this is like later in our simulation. So you see that as soon as you have some gravitational perturbation associated with the binary potential, so the two stars orbiting, this triggers some convective instability in the envelope. And later in the simulation, so this is a zoom, like it goes it goes further out, and you have this convective instability that is triggered basically everywhere in our domain except near, like along the polar axis, where not much is happening. And also, what is not shown here is that the spiral that you can guess from this figure also shear unstable. So there are some, like the shear is unstable, and this basically leads to the destruction of the spiral structure very rapidly after the beginning of our simulation. Okay, so we see that like from this criteria, and also like visually we could see that the system, everything is unstable very rapidly. I wanted to look at the contribution of this turbulent flow basically on the angular momentum transport. And to do this, we just did a Reynolds decomposition. So the turbulent velocity is just the velocity minus the mean flow, so the mean velocity. And when you plug this into the Navier-Stokes equation, you end up with you can end up with this angular momentum evolution equation. And in this equation, the first term is just the advective flux of angular momentum from the mean flow, so the transport of angular momentum associated with the mean flow. The second one is the Reynolds stress, so it's the angular momentum transport from the turbulent flow. So this is the viscous term that I will not discuss. And this is the term associated with the gravitational torque, which is typically extremely small, except very close to the binary. So we will also forget about this. So just focus on these two terms. Oh, okay. So yeah, so this video is just an illustration of this. So this is the amplitude of the turbulent velocity, just to illustrate it. Yeah, so this is the U prime I showed before, so the amplitude of the U prime in all directions. So you can see that clearly the turbulent velocity is non-zero, and it's very, very turbulent everywhere in our domain. So yeah, so that was not supposed to be so complicated to access. So yeah, so it's not very important, it's fine. Oh, okay. Yes, thank you. Okay, so now if you look at these two quantities that I showed before, so sorry, this term associated with the mean flow and this term associated with the turbulent flow. So this is what we have here. So on the left side is the contribution from the mean flow, and on the right side from the turbulent flow. So first, let's briefly look at the effect of the mean flow on the angular momentum transport. So what you can see, so in blue, when it's in blue, it's the angular momentum is transported outwards, and when it's red, it's transported inwards toward the binary that is at the center. So you can see that the mean flow leads to an angular momentum transport outwards in a disk-like structure. And the thickness or the opening angle here will depend this time on the amount of angular momentum that we have initially in the envelope. So it's outwards in a disk-like structure and inwards along the rotation axis, or the orbital rotation axis. And as for the turbulent flow, the structure is slightly more complicated, of course, but depending on the model, the amplitude of this turbulent flow can be sufficient to locally reverse the direction of the angular momentum transport. So it's possible that in some cases, if you sum the two contributions, you will not have this outflow in a disk-like structure, but you locally would have some inflow. But for most cases and at most times, the turbulent flow actually does not contribute that much to the angular momentum transport. And just to finish, just a quick word on something else we looked at. We wanted to look at the typical length scale of these convective eddies. And to do that, we used a technique that is often used in experimental fluid dynamics. And this is this normalized autocorrelation. Well, you can read it if you want, but it doesn't really matter. So it's the normalized autocorrelation function. And if you integrate this quantity over all shift in radius, you get this, what's called the integral scale. And this quantity will represent the typical eddy or convective eddy length scale with a larger contribution for the larger scale. But yeah. And so so usually you should integrate this up to infinity. But actually, what people noticed, like in most of the time in experimental fluid dynamics, is that this tail here, so after this quantity reaches zero, it actually contains information that is not related to the turbulent flow. So what people do usually is that they integrate this quantity only up to the first zero crossing of the autocorrelation function. So like this. Okay, so when you do that, so I've done that in 3 separated regions. So the first one is close to the binary. This one is in a region further out, and the last one is far from the binary. And I've done this because usually the expression I showed before is only valid for homogeneous turbulence, which is not the case in our simulation. Okay, so when you do this, you can measure the average, the typical length scale, depending on the model and depending on the region. So close to the binary, far from the binary. And as you go down here, so the C has a low amount of angular momentum initially, and A has a large amount of angular momentum. So the first thing you can see is that when you go further out, so far from the binary, the typical length scale of the turbulent, of the convective eddies increases. So this was expected, of course, because when you are far from the binary, the gas is almost non-stratified. So nothing prevents the eddy scale to be contained in a small length scale. So close to the binary is very stratified, so it prevents the turbulent eddies from being too large. And we also see that this typical convective length scale depends on the amount of angular momentum that we inject initially. So we'll skip this one. And for what you can see typically is the more initial angular momentum you have, the smaller the eddies, the convective eddies. And that means that the angular momentum profile that we inject initially has a stabilizing effect, so it decreases the size of the convective eddies. And another thing you can see is that if you decrease the angular momentum in the far from the binary, you go from model B to model C, you see that you don't have this change, this increase of the eddy length scale. And this is just shows that if you have zero stratification, basically, if you don't have density gradient, it does not mean that you should have an eddy length scale that goes to infinity. Actually, that limit value is probably associated with the size of our numerical domain. So I will just finish with a summary. So we tried to answer 3 questions. So first, how the binary evolves. So does it contract, does it expand, and on what time scale? So we find that when we allow for accretion, the binary contracts on a time scale that is much shorter than what was expected, so a thermal time scale. But of course, if you allow completely accretion, then some mechanism has to release the pressure near the binary. So if it's jets, for instance, you would have to account for the feedback, which we did not do. And when you don't have accretion, it's the gravitational torque that will control the binary evolution. And this time scale is initially short, but it increases all the time, and eventually it reaches the thermal time scale, and even it can surpass it. Then we looked at the typical frequency for the short-term variability of mass accretion. And we find two characteristic frequencies, so 2 omega and omega over 5. So this is the orbital angular frequency. And these two frequencies are also in circumbinary disks, but there is a small difference in what it means. So for circumbinary disks, this frequency is the orbital frequency of overdensities, and in our case is the frequency of formation and destruction of overdensities. We've seen that we have formation also of these overdensities, and that because they trap the gas, they will lead to the amplification of the envelope eccentricity. And finally, we looked at the angular momentum transport in the envelope, and we saw that it's basically a contribution from the mean flow and the Reynolds stress, or the turbulent flow. And usually this turbulent flow does not contribute that much, or is negligible comparable to, in comparison to the effect of the mean flow. And we saw that in total, it usually leads to outward angular momentum transport in a disk-like structure, and inward about the polar axis. And the paper will be submitted soon. Yeah, that's it. Okay.